Awesome. Oh, is my volume still really quiet? Let me see if I can fix that. Did that help? Is it a little bit louder now?
Yeah, I can hear you now.
Oh, awesome. Yeah, a different setup today. So there were a few technical issues with that, but we should be good to go now. So let's go ahead and we can get started on the first problem. So here we've got a practice problem with a proof. So here we're asked to prove that the product of an odd integer and an even integer always gives an even integer. So if you want to go ahead and take a minute or two to kind of think about the problem, think about the definitions, what do we need to define for odd integer and even integer, and go ahead and take just a minute or two and get started on the problem, and then we'll go through the solution. Cool. So hopefully that was enough time to get a little start. So let's figure out how we could start proving this statement. Well, the first thing is we need to introduce some kind of variable to represent this odd integer and this even integer. So let's give each of those a name. So let's just say let's just say x be an odd integer. And y be an even integer. That are given. So we have some odd integer and some that should say even integer that are given. So if someone wants to throw up in chat, so what could we say? How could we write x and y then? Or if you just want to raise your hand and unmute, yeah. So it looks like, yeah, for x, we've got in chat that x is equal to 2k plus 1, and we need to, for some k that's an integer, And then we've also got that y would be 2k for some k in integer. Yeah. So does anybody see a problem with how we've defined x and y here? Or is this a fine way to define it? If someone wants to like raise your hands and go ahead and say what you think. Yeah, so it looks like we've got several answers in chat. Yeah, you can't use k for both. Yes, because they're not necessarily the same value. So this is something we always have to remember when we're introducing new variables. Using definitions of odd and even integers is we can't use the same repeated variables. This k and this k aren't necessarily the same value. So we need to introduce some other variable for this other integer. So let's just say m for this one. So y is equal to 2m for some m an element of z, because we have to have two different values here to represent all odd integers and all even integers. Oh, yeah, that's a great question. So Brendan asked, is there a difference between for all k or for some k? Yeah, I guess another way I could have said for some, this is kind of implying that there just exists, like the for some, that just really means that there just exists at some integer. So here we're really meaning that to mean like there exists. So that might have been made it a little bit more clear. I don't know what Adobe's doing. What is going on? Can't erase. Yeah, so that, yeah, might have been a little bit better to say there because that was a great question. So we're just saying that there exists some integer k such that x is equal to 2k plus 1, and there exists an integer m where y is equal to 2m. And then what we're asked to prove, so we're asked to prove that the product of an odd and even integer is always even. So we want to look at what's the product of x and y equal to. So then x times y, well, we can just plug in the values. So x is 2k plus 1. Y is 2m. And then we just work out what this value gives. So this is a 4km plus 2m. And we can rewrite this. We can factor out a 2 from this equation. And why we might do that? Well, because we're trying to look for this even integer. So we're in this process, we're asked to prove that x times y is an even integer. So we're looking for some way that we can represent what an even integer is. So we're going to factor out the 2. So that's 2 times 2km plus m. And then this is just equal to, let's say, 2n, where n is equal to 2k m plus m. And then how do we know? So when we have to prove that this is an even integer, what's the other thing we need to say here in this final step before we can conclude that x times y is an even integer? Yeah, so Brendan in chat, perfect. We need to say that this n is an integer by closure of multiplication and addition. So and it's an element of the integers by closure, multiplication, and addition. And that is what lets us say that we have an even integer. So then x times y is even, and we're done with the proof. Now you just use the square box, or you could do QED or something just to denote that we're done with the proof there. So any questions on any parts of this problem? There'll be similar problems that you'll have on the next homework. So any questions on kind of the structure of this one?
So the first step of the proof is writing down the sentence, let x be an odd integer. If you don't have something like that, if you just go right to saying x equals 2k plus 1 and you say that they're both integers, is that omitting an important step, or can you still understand that x is an odd integer by writing down that equation?
I would recommend writing down just this statement, just because you kind of want to signify, like, proofs are kind of like you're writing this to some other reader who's going to read this and be able to follow every step of your proof. So you kind of just want to signify that, hey, I know this is, like, why did we write this down? And why did we write this down? Well, this is the definition of an odd integer. This is the definition of an even integer. So you kind of want to pull these two parts of the proof statement into your proof somehow. So you could have just said, let x equal 2k plus 1. By definition is odd, and y equal 2m is by definition even. And then look at x times y. But you just want some place to signal that, hey, I follow the proof statement. I know what an odd integer is, and I know what an even integer is, just to make it clear. And that's something you can do in all your proofs. Is kind of good practice.
Okay, sounds good.
And then, yeah, I had a question. We got 2k and 2k plus 1 for the definitions of even and odd. Yeah, so we just applied those definitions. That's how we came up. And it looks like we've got Jake, raise your hand so you can go ahead and ask your question.
Yeah, so my question was, I know when we were learning this, they gave us this skeleton for proofs. Oh, it might have only been for inductive proofs, but they wanted us to do like a base case and like write our hypothesis. Is that the same situation here?
It's a little bit different. So that structure is for an induction proof.
Okay. Okay.
An induction is you're usually know a proof's induction if you're asked to prove it for like all integers or like any such n.
Trân trọng giới thiệu bread of the y.
And then yeah, so you usually have a base case there, and then you'll do an induction, and yeah, we'll have this whole process here.
Okay, I got you. Thank you. Sorry about that.
A little bit different here, but you could kind of create like a skeleton for those type of proofs as well, where this kind of part is really just like restating the statement, right? But with variables. So we introduced some variables x and y, and that's basically all we did in the first line. And then basically we just apply definitions. So what does it mean to be an odd integer? What does it mean to be an even integer? And we're always going to do these in lots of proofs, where we're going to need to open up what is the definition of this. And then kind of the rest of the part is you just want to, I guess kind of in general, you just want to like, this is just kind of more your actual like the work of the proof, where you just want to, I guess, kind of like show the conclusion is true. It's hard to make this end part a little bit more general because it often depends on the type of problem. But this first kind of two parts, that's going to pretty much be the same always. Yeah, great questions. And then there's this end thing. Just restate the conclusion is kind of this end part. Just letting your reader know that, hey, I proved what I was asked to show. We were asked to prove that product of an odd and an even is always even, and thus, from our conclusion, x times y is even. And that'll always be kind of the same in any of your proofs. Any other questions on this one? Awesome. So let's go ahead and move to the second problem. So here, we've got a problem on induction. So kind of like Jake was talking about earlier, there's some skeleton of how to do an induction proof that we're going to want to follow. And we always want to do that for every induction proof. So here we're asked to use induction to prove that for each integer n greater than or equal to 1, we want n to prove that n cubed minus n is divisible by 3. So for induction, we've kind of got this kind of 4-step skeleton that we're gonna kind of go through. So the first kind of step we want to think about is the problem statement. And this is kind of similar to what I was talking about in the last proof, where we kind of want to restate what we're really being asked to show here. So does someone want to volunteer either in chat or raising their hand? What might we say for the problem statement in this problem?
Maybe we can use the quantifiers symbols, like for all integer n greater than or equal to 1. Second part, let's see. We can say divisible by 3.
Yeah, and what does it mean that it's divisible by 3? What's another way we could kind of say that by using the definition?
If we, I'm not quite sure.
Yes, we've got, okay, so we've got some suggestions in chat. We could say, hey, mod 3, it's 0. Yes, that's the right idea. And what does it mean, mod 3, that it's 0?
Can I answer?
Yeah, sure. Yeah, go ahead.
It's like that n cubed minus n is equal to some number times 3.
Yeah, perfect. So it's equal to like 3k.
Yeah.
And I guess I could maybe write there, for all n greater than or equal to 1, there exists a k such that n cubed minus n is equal to 3k. And then something we always want to do with induction. So another way we can kind of say this is we want to introduce some proposition. Is usually the notation that we use. You may recall from the lecture that we restated it also as some p of n. So we're going to prove this. This statement is true for some value of n, and that's kind of what Pn is. And so versus P of n is just going to mean n cubed minus n is equal to 3k. And we want to prove that Pn is true for all n greater than or equal to 1. So this is what we're looking for with our problem statement. Make sure you have some Pn. And then what does that mean? And here, I guess, there exists a k such that holds. And so that's kind of what we're asked to prove. And then this kind of leads into the next step. So does anyone want to just type in chat, what would be the next step in our kind of induction proof skeleton? Okay, Brandon's asked, I wrote this. Does this work? So for all n z, n is greater than or equal to n is greater than or equal to 1, n cubed minus n mod 3 is equal to 0. That does work, but we want to kind of open that definition up further because it's sometimes hard to work with just mod on its own. And so what does it mean that something is mod 0? Well, it means that when you use the division algorithm, the division theorem, that the remainder is 0, and we can rewrite the expression as some 3 times a number. So yeah, that's a great start. And then you just want to open up that definition further for mod using the division theorem. And then, yeah, Jake, so the next step would be base case. Yeah, we want to prove P of 1. And this is almost always going to be the case. My stylus is not working. Let me fix this for just 1 second. But yeah, so we're always going to start with whatever the smallest value is. Oftentimes it's going to be 1, but it depends on the problem. So we always want to look for what's the smallest possible value of the n that we're given. Here it's 1. So our base case. We want to prove that P of 1 is true. So how can we show P of 1 is true? Well, we just need to show that exists some k such that n cubed minus n is equal to 3 times that value. So, well, P sub 1, what does that mean? So let's just plug in 1 for n. So that's 1 cubed minus 1, and that's equal to 0. Right, and is 0 divisible by 3? Yeah. Why is it divisible by 3? Well, this is really just 3 times 0. That's our integer k. So we've shown that it's divisible by 3. So we proved our base case. Now, whenever you're doing these base cases, they should feel somewhat simple. You shouldn't have to do too much work in order to get the base case to prove. Oftentimes it'll be just really simple, just like, oh yeah, of course the base case is true. And that's kind of what's nice about induction, is these first couple of steps, they almost always work out the exact same for each kind of problem. We have to write k is an integer of z, right? Yeah. So here, yeah, perfect. Yeah, I didn't write that up here. Great observation, Brendan. Yeah, where k is an integer. And then here we know that 0 is obviously an integer, so this works. Any questions so far with our start with induction? Why is k equal to 0? We're just looking for some, because we want to show that P of 1 is true, right? So we want to show that we can rewrite that 1 cubed minus 1 is divisible by 3. And how do we show that? Well, we need to show that it's equal to 3 times some integer k. And if 1 cubed minus 1 is equal to 0, we can rewrite that as 3 times some integer, which happens to be 0. So this is just showing that this divisible by 3 portion. Awesome. Any other questions? Cool. So let's go ahead to the next part. So we've done the problem statement, we've done the base case. Now the other part of our skeleton is the induction hypothesis. We're always going to use this whenever we do induction. Now remember, the induction hypothesis is where we're going to make some assumption for some general value. And then with induction, we prove, in the next step, we're going to prove it's true for the next value. So does someone want to make a suggestion for what is our induction hypothesis for this problem? You can just go ahead and raise your hand if you think you know it. No guesses? Okay, so we've got to get, we want P of n plus 1. Almost, not quite. So that's a good idea. We are going to do that with this induction, in induction. But that's where we're going to kind of use the induction step, is we're going to show that P of n plus 1 is true. But with the induction hypothesis, we assume that the hypothesis is true for some value of n. Yeah, so like Jake suggested, we could assume it's true for P of n minus 1, and then prove it's true for P of n. Or we could assume it's true for P of n, show it's P of n plus 1. And here, the math will work out slightly better if we assume P of n is true. So we're just going to go ahead and make that assumption. So our induction hypothesis is we assume that P of n is true. In other words, that there does in fact exist in K in the integers such that n cubed minus n is equal to 3 times K. And we're always going to do something similar to this when we do induction. We'll either assume that P of n is true, or assume that P of n minus 1 is true. Some assumption about some previous values, and then we're going to prove it's true for the next one. And one way I like to think about this is kind of like dominoes. So we set up a line of dominoes. Now we want to prove that all the dominoes fall down. So the base case, we show that the first domino falls. Because we need the first one to fall in order to show that we can make all the other dominoes fall. So we prove the base case, we prove the first domino falls. And then with the induction hypothesis is we just assume that any domino in our line falls. We're going to prove that the next domino must fall. And then if we can prove that one falls, if we assume one falls, then it knocks over the next domino, then we've proven that all the dominoes must fall over. And that's kind of what we do with induction. So our next step here is going to be the induction step. And that's where we're going to prove that the next domino falls over. Or we're going to show that if P sub n is true, then that implies that P of n plus 1 has to be true. So let's start with this. So if we know P of n plus 1 is true, got a question in chat. Yeah, so if we assume P of n minus 1 is true, then we prove P of n. Yes. And then we could also assume P of n is true, prove P of n plus 1. Yes. Those are the two most often used cases with induction. Sometimes one works out better just algebra-wise than the other, but both are completely valid. So you can pick any of them to use at any given point. You just assume that some value is true, and you just have to show that it's the next value of n it must be true for. Yeah, so yeah, great question there. So here we've got that we want to show P of n plus 1. That n plus 1 is true. So what does that mean? Well, we need to be able to show that there exists some k such that, in this case, we want n plus 1 cubed minus n plus 1 to be a multiple of 3. So what we want to conclude. So let's go ahead and just write down what n plus 1 cubed minus n plus 1 is. And we can start kind of playing with the values and seeing, we're looking for some point where we can use this induction hypothesis. So we want, at some point, we want to use this statement in this induction step. And we're really trying to find when we're going to be able to use that. So we can just start by opening up this algebra. Here, n plus 1 cubed. If you remember how kind of the general form for cubics here, this is going to be n cubed plus 3n squared plus 3n plus 1 minus n plus 1. Just recall that you can expand quadratics, cubics, quartics, and the such really fast by looking at the coefficients with Pascal's triangle. So if you just write down Pascal's triangle, so for a cubic, these are the coefficients of the values that we have. So we've got n cubed, so we just write n cubed, n squared, n, and 1. And then the coefficients in front of those values are just the values from Pascal's triangle, where each previous values are just the sum of the ones above. So for this line, we get 1 plus 2 is 3, 2 plus 1 is 3, and then 1 plus 1 is 1. And so those are the values for our coefficients here. Just something to recall, if you haven't seen that before, that's perfectly fine. You don't need that. You can definitely work these out. But just something, if you're doing some of your algebra review for this class, is a little handy trick to know how to use. And then we can just kind of simplify this expression. So we get n cubed plus 3n squared plus 2n plus 1. Oh, not plus. Yeah, because the plus 1 and minus 1 cancel each other out. And looks like, any more questions? No, cool. And then what can we do here? Well, we can factor an n out. Actually, that's not going to help us. How do I know that's not going to help us? Because we're looking for some point where we can use the fact that n cubed minus n is equal to 3k. So we're looking for some point when this is going to be useful. So we don't want to quite factor and do all the simplification. But where is this going to be useful? Separate 2n into 3n minus 1. Yes, that is the perfect next step, what David said in chat. And that's a great observation. 2n is really 3n minus n. And now we can kind of reassociate these values. So we bring n cubed minus n. And then we've got plus 3n squared plus 3n. And then what do we know about n cubed minus n? Well, from our induction hypothesis, they're going to assume it's true. We know that p of n is true. So we know that n cubed minus n is equal to 3 times k. And this line, and it's sometimes nice to really point this out, that this is by the induction hypothesis. Is how we get from this previous line to the next line. And there's always going to be some point in our induction step where we use this fact. So always be on the lookout for when we can use that induction hypothesis. And then, remember, we wanted to show that p of n plus 1 is true, that it's divisible by 3, or that it's 3 times some k. So this is just 3 times k plus n squared plus n, since we can factor a 3 out. And this is equal to some 3 times c, where c is k plus n squared plus n. which is an integer by, yeah, because of closure of multiplication and addition. Yeah, somebody said there's also square in there. Yeah, so squaring comes from closure of multiplication. If you kind of want to see that, this is equal to k plus n times n plus n. So n squared is really just, squaring is really just repeated multiplication. And c is an integer by closure of multiplication and addition. And then we would just add kind of one final statement at the end of our proof just to show like where we restate the conclusion. So we might add a statement, kind of running out of room here before the next problem. So then at the end, we would just say by induction, it has been shown that P of n holds true for integers n greater than or equal to 1. And that would just be kind of the conclusion, wrapping up our proof. So any questions with this? This is really the meat of induction proofs, stating the induction hypothesis and doing this induction step. Can definitely take some time. So any questions with any of the steps that we did in this problem or about induction in general?
Is there a real life example for induction proof?
Like, what do you mean by real life example? Like something in the real world that we kind of use induction for, or?
Yeah, some kind of, I don't know, something concrete to think about, like how this will use this to buy bread, or I don't know, what exactly is this? Is this applied? Is this like in computer science for some kind of algorithm?
Yeah, induction is used all over the place in computer science. And in some of your later classes, you're actually going to see that induction is really recursion. Those two are really closely linked, induction and recursion. So if you just think about any recursive algorithm that you've ever written, that's really induction. Just normally with recursion, we usually start with the large problem and we go to a smaller one until we get to the base case. So recursion, we usually start with some large n, and then we solve for what's n minus 1, n minus, we solve all the way down until we get to the base case. Whereas induction, we're working our way up. We're proving that it's true for n equals 1, and then we just prove it's true for some general n. Yeah, really good question. So this is hugely important thing in computer science, learning induction. Any other questions on any of our induction steps here? No, looks like we're good. So definitely get some practice with these induction proofs. Just work on lots of examples of these. There's some good examples in the textbook as well, but definitely just try to work out a lot of examples because that's really how you're going to learn how to do these induction proofs. There's a question in chat. For this question, would it have been correct to prove P of n plus 1 is equal to n cubed minus n, or just 3k? It would not have been correct to prove that it's equal to n cubed minus n, because we wouldn't be able to conclude anywhere that this is equal to some n cubed minus n in our proof statement. We have to, because we have to prove that it's divisible by 3, so we have to show somehow that we can take n plus 1 cubed minus n plus 1 and rewrite it as sum 3 times k, just because that's what the problem statement was asking for. Great questions. Yeah. So if there's no others, let's go ahead and we'll move on to the next problem. So here we've got another proof problem. So here we're asked to prove if n is not divisible by 3, then n squared plus 2 is divisible by 3. And we've got about 10 minutes left. So I'm just going to kind of work through this one, just to make sure we can get through it in the time. So we want to, if we kind of want to think about that outline that I talked about earlier with our first number proof that I believe Jake was asking a question about. So the first thing we want to do is kind of restate our problem. So here we've actually introduced this value n. So so we're just going to say about an integer and not divisible by 3. Be given. So that's kind of our restatement of our problem here. This is really kind of like our, yeah. Restate problem. Next step would be open up the definition. So what does it mean to have an integer not divisible by 3? So anyone, just in chat, yeah, quickly, yeah. So yes, so David's correct. It could be not 3n plus 1. I think you mean like 3k plus 1. Using the division theorem, right? We can. The remainder in the division theorem is not going to be 0, but there's also another case. Yeah, 3k plus 1, 3k plus 2. Yes, perfect. So by the division theorem, either n equals 3k plus 1, or n equals 3k plus 2 for some integer k that's an integer. And this part was really using our definitions, right? That's always the second part. So we want to like, what does it mean that n is not divisible by 3? Well, we open up that definition, use the division theorem, and this is what it means. Now we want to do the bulk of the proof, right? We just want to kind of work out, starting with n is equal to 3k plus 1, that we can show that n squared plus 2 is not divisible by 3. And so here, how do we write this in simple form? What do you mean by that with simple form? Oh, yeah. So here we could say by the division term, we could have put like there exists a k, it's an integer, such that n equals 3k plus 1 or n equals 3k plus 2. If you wanted, there exists. It's perfectly fine to put for some k as an integer as well, but that would be another way to use it in simple form. And the for all n is just kind of implicitly implied by saying that we are given some unknown integer. And by being given an unknown integer, we're proving it for all n. Great questions. And then for this problem, so we've got two cases here from the division theorem. So case 1, n is equal to 3k plus 1. And then we want to look at what is n squared, or what is 3k plus 1 squared. We want to look at this value and conclude that this value is divisible by 3. Or in other words, that it can be written as sum 3 times k for some integer k. So n squared plus 2 is equal to, we just substitute in 3k plus 1 for n, 3k plus 1 squared plus 2. And that's 9k squared plus 6k plus 3. Yeah, Brendan, that would be correct for symbol form. But when we do the proof problem, the one thing you do want to make sure you is that we have to pick some unknown integer. So we have to just let an integer n be given at some point in the proof statement. But yes, that is how you rewrite the statement, just generally in like a symbol notation. So we've got this n(k) squared plus 6k plus 3. We want to prove that this is divisible by 3. That's pretty easy to see here because we can just factor 3 out. So that's going to be 3k plus 2k squared plus 2k plus 1. And this is 3, we can call it sum c, where c is equal to 3k squared plus 2k plus 1. And then remember, we have to prove that c is an integer, right? And c is an integer by the closure properties. By closure of multiplication. And addition. And then we would have some case 2, where we would show that this works out for n equals 3k plus 2. It works out really similarly. You'll see that there's a spot if you go through the algebra where there's a spot you can factor 3 out, then you can show it's divisible, and then you just need to write a final statement at the end saying, therefore it's true that if n is not divisible by 3, n squared plus 2 is divisible by 3. And that would kind of wrap up the rest of that problem. I'll just leave that as an exercise for you all to kind of work through and get a little bit of practice. It'll be nearly identical to how case 1 kind of worked out. And then the last problem that I wanted to get through is just this final problem, just on, this one won't take too long, just a problem on some counterexamples. And so we've got these two statements. If you like computers, you would love computer science. And if you do not like computers, you would not like computer science. So first question, if someone just wants to go ahead and answer, are these statements contrapositive of one another? Yeah, I can see in the video chats, it looks like people are shaking their head no. Yes, these are not contrapositives. Can somebody tell me what they are? Yes, this is the inverse. This was just one we kind of wanted to clear up. We've seen on some of the homework where there might have been some confusion about inverses, contrapositives. Want to make sure that, yeah, these two statements are inverses, right? If we have P implies Q, the contrapositive would be not Q implies not P, inverse not P implies not Q. And then the final part is it just asks what traits must a counterexample to each statement have? So does somebody quickly just want to unmute themselves or raise their hand for what might counterexamples, if we were trying to disprove these two statements, what would we have to show?
What, that someone likes computers but doesn't like computer science?
Yes, that would work for the first problem, for the first statement. We need someone who likes computers, but doesn't like computer science. And then what about the second one? So any volunteers for the second part? For a
So-
counterexample to the second statement.
If you do not like computers, but you do like computer science.
Yeah. So just remember here, when we're looking for counterexamples, this is true for any of our proofs. For trying to disprove something, we want something where the hypothesis is true, but the conclusion is false. So notice in both cases, we're looking at, in the first case, we're looking for somebody who likes computers, doesn't like computer science. Second case, if you do not like somebody who doesn't like computers, but they do like computer science. We're looking for counterexamples. And so that takes us about to time. So if you do have any more questions, please stop by office hours. And then for those of you who haven't finished or took quiz 1 on Tuesday, don't forget that the makeup quiz 1 is due today, and you have until 8 p.m. to have it submitted, which means that the latest you should be starting at 6:45 if you want the full time. Awesome. So we're done with this discussion for today. So I hope you all have a great rest of your day.
Thank you, James.
Thank you.
Thank you. Have a good day.